Hello everyone, welcome to our new lesson, lesson 9-4, graphing rational functions. I hope you did fine in the previous lesson 9-3. Remember we started unit 9 a couple of weeks ago before the spring break, and we did our first lesson last week and second lesson. It's more about, again, graphing key features of rational functions, talking about vertical, horizontal asymptotes. That's all same. So this lesson is a little bit just like the previous one, talking about the key features of the graphing rational functions, and we'll still talk about vertical and horizontal asymptotes, but this time it will be in different version. It's like, you know how we have a function, rational function as this, 2 over x plus 4 minus 3. We mentioned what are the vertical and horizontal asymptotes. We mentioned the graphs and the transformations. Same thing today, but this time we will not have it as a fixed fraction like 2 over x plus 4 plus 3. Instead, we will have an improper fraction way, and we'll talk about how do we again find the key features of the given rational function. Okay, so here's the table. By the way, we are on page 477, so make sure you open the page 477. We will go over the given table first, and we'll move on with the question. So first, let's see, if we are given the rational function in the a of x over b of x form, like numerator over denominator, something like that, x squared over x cubed plus 1, what are the key features? Okay, if we have so, we can tell that first, number 1, if you are looking for the vertical asymptote, the given thing, something over something, numerator over denominator, top over bottom. If you are looking for vertical asymptote, you will just look at the denominator and set it equal to 0 and solve for it. That's first. Second, if you are looking for the horizontal asymptote, looks like we have three cases, A, B, and C. 2A, 2B, 2C. For the vertical, it is simpler. You just check the bottom of the fraction, set it equal to 0, solve it, get as much as you can. That's the vertical asymptote. Horizontal asymptote is you are gonna compare the numerator with the denominator. First, when you check the numerator with the denominator, if the degree of the numerator is greater than the degree of the denominator, then the horizontal asymptote will not appear. We will have none. No horizontal asymptote. Second, if the degree of the numerator, ax basically, is less than the degree of the denominator, then we will have a 0. Y is equal to 0 will be our horizontal asymptote. That's case 2. Or the third case, if the degrees are same, the numerator equals to denominator. Remember how we find the degrees, by the way. The highest exponent in the given thing is the degree. If these are same for top and bottom, then you will just compare the coefficients of top and bottom and get the ratio. Whatever is that, that's the answer. Okay, that's the case. One more time. For the vertical asymptote, we have one thing. You check the denominator, just like we did last week. For the horizontal asymptote, we have 2a, 2b, 2c. What if degree on top is greater? Then we don't have any. What if the degree on bottom is higher? Then we have y is equal to 0 as the horizontal asymptote. What if the degrees are same? You just get the ratio of the coefficients, the leading coefficients. Whatever the ratio, that's the answer. That's how you say. Okay? Okay. Alright, so this is what it is. So we will see now in the given questions. Okay? So question 1. Graph with no horizontal asymptote. Okay, let's see. So we are gonna check the attributes, the key features one more time. X-intercept, Y-intercept, vertical, horizontal. We will just check them. By the way I do may differ from the one the book says, so I will just do it here on the white page here. You just copy it on somewhere available, or if you want you can fill the gaps. It's too much wordy over there, so I didn't prefer that. I'll just do it here. You can copy it somewhere on a separate sheet, also fine, but make sure after this you go over the lesson and fill the gaps, okay? That way you will learn better, and it will help you much more towards the next year class, okay, for pre-calculus. Okay, let's get started. X-intercept. So remember, for x-intercept we say replace y with 0, right? So f of x will be switch with 0. But shortcut, if it's asking x-intercept, check the numerator and get that equal to 0. So x cubed will be equal to 0. If you are looking for x-intercept, the other way to say 0 of the function, you may hear different ways. Then you will check the numerator, the top, and that will be equal to 0. Since we have the x cubed on top, you will just get that equal to 0. Guess what? If you take the cubic root of both sides, x will be equal to 0, will be our x-intercept. So 0 will be our x-intercept over there. For y-intercept, it's even easier. Just replace the x with 0 everywhere here. So we are basically calculating f of 0. Okay, if you do that, that's a 0 cubed over 0 plus 2 over 3. That's also 0. So we got y equal to 0 is also y-intercept. Looks like we have 0, 0 is the origin, is both x-intercept and y-intercept of this rational function. For the vertical asymptote, remember what I said. Check the denominator. If you check the numerator, that will tell you about the x-intercept. If you check the denominator, that will tell you about vertical asymptote, okay? So set the denominator, which is x plus 2 over 3, equal to 0. Solve for x. You know how you subtract 2 over 3. That's negative 2 over 3. Here will be our vertical asymptote. That's it. It might be more than 1 based on what's the degree in the denominator. Okay, you have only one here. Horizontal asymptote. Remember rule 2a, 2b, 2c. Since we check the degrees on top and bottom, the degree on top is 3, right? And the degree on bottom is 1, and I can tell the degree of the numerator is greater than the degree of the denominator. Since it is 3 to 1, I can tell the horizontal asymptote will be here, none. Or as you can imply from the title here, no horizontal asymptote, because the degree of numerator is more than the degree of the denominator. So in that case, we do not have we don't have any horizontal asymptote. Remember the case A. It's just this one. Okay. For graphing, let's just put this one in the calculator. Today I'm going to use the Desmos. So I will put this together here as x cubed over slash, not like that, like this one, x cubed over, what did we say, x plus 2 over 3. So we will have an x plus 2 over 3 here. There we go. This is our function. Okay, so as you see, we don't have any horizontal asymptote. Nothing is crossing or cutting this function, but we do definitely have a vertical asymptote here. Let's put what we have. It was x is equal to negative 2 over 3, right? Yeah, there we go. So we have the vertical line here going all the way up, but never touches the left branch that we have, or even the right branch here. It's just like limiting both are crossing each other's sides. So this is how the graph will look like. Okay. All right. This is our first question. Okay, example 2 is very quick. We have a word problem here. Let's read the question. It says Young's rule can be used to estimate the dosage of medicine to give a child, or if you know the adult dosage of the same medicine. Young's rule can be written as y is equal to ax over x plus 12. A is the amount that for adults X is the age. The letters are important. X is the age of the young people, and A is the usage that we have for the adults. So first, find the function. Question says that find the dosage for a 12-year-old. Or before that, in question, we are given that 200 milligram is the adult usage. That means A is equal to 200. This question is on page 478 towards bottom. Okay, so if you look at the function now we don't have A anymore. It's more specified. It is 200x over x plus 12 is our rational function. Okay, this function represents how much a young child should be given when it's compared with the adult dosage of the medicine. Okay, alright, so let's answer those. First part, it says find intercepts, asymptotes, and behavior. Looks like we have something new. And behavior. Let's start with x-intercept. Y-intercept then. Vertical asymptote, horizontal asymptote, and behavior then. When we put this 200x over x plus 12 in the Desmos, it's gonna be a graph like that. You can definitely say what are the x and y intercepts and the vertical and horizontal asymptotes here, but let's just use the graph for verification. We will just do it by ourselves. Remember, for x-intercept, you just check the numerator. That'll equal to 0. That gets you x is equal to 0. You know how to do that. For y-intercept, you just replace the x with 0, as you know. It's just gonna be 200 times 0 over 0 plus 12 is just 0 again. So y will be equal to 0. So again, just like the previous question, we have origin as the x and y intercepts. Okay, for vertical asymptote, remember the rule. You this time check the bottom. X plus 12 will be equal to 0. That gets you x is equal to negative 12 is your vertical asymptote. Horizontal asymptotes, check the degree of the top and bottom. Degree of top is 1 and degree of bottom is also 1. We have x and x. When we check the degrees, they are same. And this goes to rule 2 to see when the degrees are equal, you just get the ratio of the leading coefficients. That is 2c for horizontal asymptote. Since the degree is 1 of both, the coefficients are 200 on top and 1 on bottom. So you just get y is equal to 200 is your horizontal asymptote. That's it. Let's verify these all four informations from the graph. Horizontal asymptote, as you see, is 200 here, a horizontal line. The vertical asymptote is negative 12 right here. You see the branches are never crossing, and we have our butterfly here. The picture, the graph. X-intercept, we said 0. Y-intercept, we also say 0. It's right here at the origin. It might be something different next time. And behavior. That means when x goes to infinity, when you go right, where is this function going, up or down? You see, when x increasing, you see the right branch, it's going this way. It's not going to positive infinity, it's not going to negative infinity, unlike logarithmic exponential functions. So it's just going to 200. So this time, f of x is going to 200. Or when you go left, on the left and tail, to the left, you see how we go here? The function is also going to 200. That's our end behavior. To the left, the function goes to 100. To the right, the function also goes to 100. One last thing. I think I mentioned this last week. End behavior is directly correlated with horizontal functions. Horizontal asymptotes. What you have horizontal asymptote will tell you about end behavior too. Okay? That's the deal. So that's the end of the question. And part C is easy. Part C is more algebraic. It says, I'm going to write a C here. Find the dosage for a 12-year-old child if the adult dosage is 200 milligram. So basically, we are looking for a 12-year-old. So this is x, right? Because x represents the age. So we will just replace in this function x with 12. So 200 times 12 over 12 plus 12 If you do the math, I believe you will just get 100 milligram. So it's like, if your parent is using a 200 milligram of the medicine, that means you are using 100 milligram of it if you are 12 years old. If you are a little bit older, maybe it's a little bit higher dosage for you. Okay, example 2 is like this one. Let's go to example 3. It says this time let's compare the given two functions. Okay. Before that, we have an g of x function is this, and we have an h of x function here. This is the h of x function. Okay, do not confuse that. G of x's graph is this. It's not. We have two different functions. One function is given, the other's graph is given. Okay, so let's put the attributes of this one. Okay, I'm gonna say for h of x, let's find out the x-intercept, y-intercept, horizontal asymptote, vertical asymptote. We have 4, and let's talk about end behavior. Okay, at this moment you just learn from example 2. Just stop the video and do it by yourself. Fill the gaps here, like what you need to write, and check with me. Okay, so x-intercept, if you look at from the graph, x-intercept is here definitely, right? If you consider each square is 1 unit, I can tell this is definitely -2. -2 is our x-intercept. -2, 0, that's better to say. But if you just say -2, I don't mind. Y-intercept is here, that's also -2. We can show it as 0, -2. Horizontal asymptote is this line, that is 1. Y is equal to 1, and vertical asymptote is this line, that's also 1. X is equal to 1, y is equal to 1. Do not forget to represent the horizontal asymptote with y, vertical with x. Do not just put 1. Y is equal to 1, x is equal to 1 is the way. And behavior, remember, and behavior is directly correlated with the horizontal asymptote, right? So let's see, when x goes to infinity or negative infinity, where is this function going to? It feels like it's going to the same number. If you go right, the function is going down and getting close to 1. If you go left, the function is increasing and limited by also 1. So f of x is going to 1. These are the key features for the function h of x. Let's find the same for the g of x function. For this, x-intercept, y-intercept, horizontal asymptote, vertical asymptote, and behavior again. Alright, so stop the video, try to do it by yourself and compare with mine. Okay, so x-intercept, remember, you check the top for it, you make it equal to 0, you get x is equal to 2. That's it. 2, 0, you can say. Y-intercept, just replace the x with 0. That will be it. If you do this one, I think it is just -1, isn't it? Because -2 over +2 is just -1. Or from the graph here, just ignore the x's, divide -2 by 2. Short way to find the y-intercept. Horizontal asymptotes. For horizontal asymptote, again we have 3 rules. Since the degrees are same here, 1 and 1, just compare the leading coefficients of x and 2x. They are 1 and 2, so that's the y-intercept. For the vertical asymptotes, check the bottom. Since the bottom is 2x plus 2, set that equal to 0. If you solve for it, you know how you subtract 2 and divide by 2. You get x is equal to -1. That's it. That is the vertical asymptote. X is equal to -1. And behavior, when x goes to infinity or when x goes to negative infinity. Remember, this is directly correlated with the horizontal asymptote. In both cases, it should be reaching out to 1/2. These are the key features for the function g of x, and these are for the h of x. So I know example 3 wants you to compare them. on page 479 and 480. Based on what you find, just compare them. For example, for y-intercept for g of x we have -1. For y-intercept for h of x we have -2. You can say g of x has a higher y-intercept than the g of x. I mean h of x. That's the thing. So fill the gaps on this question. We will continue with the second part. Okay. All right. So that's the example 3. And let's continue with the next page. Page 480. This is the new objective. Remember how we talk about how to find x-y intercepts, vertical, horizontal asymptotes. Now, what if we would like to talk about the oblique asymptotes? This is something totally new, oblique asymptote. We will have oblique asymptote when we do not have any horizontal asymptotes. Okay? So look at this one. So we have the x squared plus 2x plus 1 over x plus 4. So this is what we will do. You know how we have the horizontal asymptote here? We have the degree the 2 and the degree is 1 here. When we compare that, the degree of numerator is more. That means we do not have any horizontal asymptote, right? But if you don't have an horizontal asymptote, that means we may have a slanted asymptote. That means it's gonna be like a slanted line, not horizontal, not vertical. It's just like a linear function, has a slope increasing or decreasing. This is what we will have. So how do we find the oblique or slanted asymptote? We have an easy rule. You know how we have functions are shown as numerator function over denominator? Same. We will just do the long division. Remember the polynomials, unit 6. We learned how to do the synthetic and the long division. We will basically do either way and find out what we have for the quotient. And that will be our oblique asymptote, like this one. X squared plus 2x plus 1 divided by x plus 4. We will just do the long division. Synthetic division also works here, don't worry. Remember how we do that. Look at the leading terms, x squared and x. If you multiply x by another x, that's an x squared. So x times x is here, x times 4 is here as 4x. If you just subtract them from each other, you just get a -2x, isn't it? And carry the 1 down. One more time. We have -2x. We have x here. X times what makes -2x? That will be just -2. So here, -2 times x is -2x. -2 times 4 is a -8. And when again you subtract it, you will just get they cancel. 1 minus -8 is just 9. Remember, we learned this one in unit 6. So this question can be written like this. You see how we got the quotient as x minus 2. We will have x minus 2 here still. Since 9 is the remainder, we will have a positive 9 over the denominator, that's x plus 4. So there we go. We just converted the way that we had before the last week. Okay, and now you see this quotient here, x minus 2. This will be your oblique asymptote. So the asymptote, the oblique, that's a weird name by the way, asymptote will be just y is equal to x minus 2. That's it. Alright, we just get it. It was asking also the x-intercept. You know how to find it. You will just set the top equal to 0 and solve for it. That's it. I just skipped that part. So the oblique asymptote is just this. You divide the function, the top by bottom, and see what is the quotient. Remember, this happens when the degree is more. When the degree is more, you don't have horizontal asymptote. Most probably you will have a oblique asymptote, and you just find it by doing the division. What you have for the quotient is the oblique asymptote. Alright, let's also see this one in graph. I would like to use the decimals. You should have it open too. So let's see what we can do for it. So here, I will just write x squared plus 2x plus 1. This whole thing will be divided by an x plus 4. Remember the vertical asymptote, right? Let's just talk about that. You know that, right? That's -4. We have 1 here. And if we are looking for the applique asymptote, looks like you see we have a line here all the way, no horizontal, not vertical. We have a slanted one here. Remember what we get for it. That was y is equal to, or just say x minus 2, it will understand. And there we go. We have the oblique asymptote right over here. How cool is it, right? Look at this. We have the oblique asymptote. When you get closer, you see the purple, I guess, or the black color with the green, they get closer all the time but never crosses. Same way all the way down here, they get closer but never crosses. Same thing for the vertical asymptote, okay? So this is it. Just divide the top with bottom and simplify, get the quotient, be happy. Alright. So on page 482, still on the same question, fill the table, that's fine. Or just, you know how it says graph question, it's okay after definitely you find the key features, x, y intercepts, asymptote. That's okay to use calculator because we don't have to actually graph and plot a lot of points and graph it. It's not gonna even help you because it's hard to catch the pattern in rational functions. So it's okay to use the graph after you find the certain key features. That will be fine for graph questions. Okay, let's finish with the very last one. Graph with point discontinuity. This is a term very new. You will be hearing this a lot when you are in calculus class. The first unit limit will be about this one, discontinuity, continuity. We'll touch this one closely a little bit, but it's more related to a little bit advanced classes. Okay, so here, if you hear discontinuity, that means there is gonna be something wrong over there on the function. It's undefined. You will just jump over that point or the line and you will continue. Here we will call it holes as well. Hole is just like the hole, the needle hole that you will have. That's the thing. So it looks like if we graph the x squared minus 4 over x plus 2 the way we do in Desmos, you will get this line, just a straight line. It's a linear function, I know. But why? Even though we have a degree 2, it should be curvy, right? But actually it is not. Let's see why not. So the thing is that, remember, the most important thing in algebra is factoring and analyzing it, right? So whenever you are given a function like that, maybe we haven't done it before but we could have done, always factor what you are given. If you factor the top, that will be definitely x minus 2 times x plus 2, right? And the bottom will be just x plus 2 itself if you factor the function. So I'm saying, yes, factor the function all the time, not to be tricked because of the discontinuities. We haven't done because we can factor but we couldn't simplify. That was okay. But here looks like we have x plus 2 and x plus 2, they cancel, and this function is actually equal to x minus 2. Even though it's a degree of 2 rational function on top and degree of 1 denominator, this is actually will look like the graph of x minus 2. And if you graph the x minus 2, it's crossing at negative 2 as the y-intercept, remember, and a straight line, except something wrong with this one. Why? If you look at this, you know, this is the x values here is negative 2, right? At the crossing number right here, negative 2. Because you cannot plug negative 2 here. If you plug negative 2, the answer will be 0 over 0. It's gonna be indeterminate. It's gonna be undefined, right? That's why we have a hole. The hole represents that we skip that point, because when we plug the negative 2, we do not get an answer. But we plug any other number like 0, like 1, not like negative 3, like 4, we always get answers. Rational numbers, fractions, real numbers, doesn't matter. But 0 doesn't give you an answer because 0 over 0 doesn't make sense, okay? So that is the discontinuity. We say the function, let's say f of x has a discontinuity. Or the other way to say whole, it might be more than 1. Depends on how many times you simplify. We just did once, that means we have only one discontinuity, only one whole. That's at x is equal to negative 2, because you check the what you have simplified, that makes this one equal to 0, right? So x is equal to negative 2. We do not have any vertical asymptote here. it indeed looks like we should have a vertical asymptote here, but actually we do not. You should check for the discontinuity first. If you have a hole, the other way to say discontinuity over there, you do not have a vertical asymptote. So instead of vertical asymptote, we only have a discontinuity here, that is just x is equal to -2. Okay, that's the discontinuity. So one more time, my suggestion is that maybe not the first page but next page, if it says discontinuity questions related to the example 5, you should definitely factor it and check if you can simplify. If you can do a simplification like that, that means you will have a discontinuity, and in that case you will not have a vertical asymptote at that point. Instead you will have a discontinuity. There will be a hole over there, the function is not defined. Okay, so that's it guys. So we discussed the horizontal and the vertical asymptotes as well as the asymptotes one more time. So watch this video carefully again and do the homeworks. Remember again, there are 2 homeworks. Please make sure you do them, okay? They are due next Sunday. So I'm also gonna give you the answers for the check questions that you should try. So the answer for page 478, the first check question on page 478 is part A, there is a 0 at x is equal to 2. Part B, there is a vertical asymptote at x is equal to 0. Part C, graph the function, you can do it, and you will see there is no horizontal asymptote. That is page 478, the first check question. Second check question is on page 479. Actually, everything is given there, I guess. Oh, it's not a check question, sorry. It's just a part of the example 2. Okay, never mind. So go to page 480. The next question is right in the middle. And you will just see h of x has the higher horizontal asymptote. H of x will have y is equal to 2 as the horizontal asymptote, whereas the g of x has the -3. Y is equal to -3 as its horizontal asymptote. Okay, now page 481, page 482 on the very bottom. The answer will be that the function f of x has a point discontinuity at x is equal to -3. Okay, so we have a hole, we have a discontinuity at -3. Alright, so you guys know what to do. If you will have any question about anything, about video, about the homeworks, and about any explanation, remember I always send you a reply as soon as possible. So I will try my best, but just take responsibility of your own learning. Okay, so do your best, and I will see you next time. See you.